There is a number that, until recently, almost no one outside of a few hundred people on Earth had ever thought about. It is not a famous number. It does not have a name you would recognize. But for the last 25 years, that single number has been quietly holding up the entire story we tell ourselves about where we came from, how old everything is, and how it all ends. And in the last 3 years, instruments built to measure that number more precisely than ever before have started returning an answer that should not be possible. Not a small disagreement, not a rounding error, a crack running straight down the middle of physics. And the people who found it are not cranks, not contrarians, not attention seekers. They are the most careful scientists alive, and many of them are quietly terrified because the data keeps getting better and the problem keeps getting worse. And the only honest conclusion left on the table is the one nobody wanted to write down, that the model we have used to understand the entire universe might be wrong. I want you to sit with that for a second, because it is easy to hear a sentence like that and let it slide off you. We are surrounded by people online shouting that everything you know is a lie, and most of the time they are selling something. This is different. This is coming from inside the building. The astronomers who spent their entire careers defending the standard model of cosmology are the same ones now standing at podiums in front of their peers, saying that they can no longer make the numbers agree. And the strangest part is that there isn't just one anomaly. There are 3 of them. 3 completely separate lines of evidence, gathered by 3 completely different kinds of instruments, looking at 3 completely different things: the light from the very edge of time, the way galaxies are scattered across the sky, and the behavior of the emptiness between them. They have no business pointing in the same direction, and they are all pointing in the same direction. So let's slow down and do this properly, because if any of this turns out to be real, it is one of the biggest stories in the history of science, and you deserve to understand it rather than just be amazed at it. By the end of this, you are going to understand what these scientists actually found, why it shook them, why some of them think it's a mistake, why others think it's the discovery of the century, and what it would mean for you, for everything from the age of the universe to the way the cosmos finally dies, if it turns out to be true. Let me start with the thing they thought they understood. Because to feel why this evidence is such a problem, you have to first appreciate how good the old picture was. For most of human history, we had no idea how big the universe was, or how old, or whether it had a beginning at all. We told stories. Then, in the early 20th century, we got telescopes good enough to start asking the question with numbers instead of myths. And one man, looking through one of those telescopes in California, noticed something that changed our species' understanding of its own home. The galaxies were moving away from us. And not randomly, the farther away a galaxy was, the faster it was fleeing. Double the distance, double the speed. It was a clean, simple, almost suspiciously tidy relationship, and it meant something staggering. It meant that the universe was not a fixed stage on which things happened. The stage itself was growing. Space was stretching, carrying the galaxies apart like raisins in rising bread. Run that movie backwards and everything rushes together. Keep running it backwards and you reach a moment where everything that exists, every galaxy, every star, every atom in your body was compressed into a single, unimaginably hot, unimaginably dense point. We gave that moment a name that was originally meant as an insult, coined by a skeptic who thought the whole idea was ridiculous. We call it the Big Bang. And the rate at which the universe is expanding today, that clean relationship between distance and speed, became one of the most important numbers in all of science. We call it the Hubble constant after the man at the telescope. It is, in a sense, the speed of the universe. Measure it accurately, and you can wind the cosmic clock backwards and calculate how long ago everything began. Measure it accurately, and you hold the age of creation in your hands. For decades, measuring it was a nightmare. The early estimates were off by a factor of 2. Whole careers were spent arguing about it. But slowly, painstakingly, the methods improved, the telescopes got better, and by the turn of the millennium, 2 completely different ways of measuring the expansion of the universe had started to converge on an answer. And here is where the story gets good, because those 2 methods come at the problem from opposite ends of time itself. The first method is the one you'd expect. You look at relatively nearby galaxies, nearby in cosmic terms, which still means staggeringly far, and you measure how fast they are receding and how distant they are. To measure the distance, you need what astronomers call a standard candle, an object whose true brightness you already know, so that by seeing how dim it appears, you can calculate how far away it must be. Nature, it turns out, provides a few of these. Certain pulsing stars brighten and dim with a rhythm that betrays their true luminosity. Certain exploding stars, a particular kind of supernova, detonate with almost exactly the same intrinsic brightness every single time, like cosmic flashbulbs of a known wattage going off across the universe. String these together, calibrate them carefully, climb the ladder rung by rung from nearby stars to distant supernova, and you can measure the expansion rate of the universe directly here, in the relatively recent cosmic neighborhood. This is the local measurement. It is the universe telling you how fast it is expanding right now. The second method is wilder, and to me, it is one of the most beautiful ideas in all of physics. Instead of looking at nearby galaxies, you look as far away as it is physically possible to look. And because light takes time to travel, looking far away means looking far back in time. Look far enough and you reach a wall. Not a physical wall, a wall in time. For the first few 100,000 years after the Big Bang, the universe was so hot and dense that it was opaque, a glowing fog of plasma that light could not travel through. Then it cooled just enough for that fog to clear, all at once, everywhere, and the light that was set free in that instant has been traveling ever since. It is still arriving, right now. It is the oldest light in existence, stretched and cooled by 13 billion years of cosmic expansion into a faint hiss of microwaves coming from every direction in the sky. We call it the cosmic microwave background. It is, quite literally, a baby photo of the universe, a snapshot of the cosmos when it was less than 0.1% of its current age. And that baby photo is not blank. Frozen into it are tiny ripples, hot spots and cold spots, fluctuations in temperature smaller than 100,000th of a degree. Those ripples are the seeds of everything. They are the slightly denser regions that gravity would later pull together into the first stars, the first galaxies, the great cosmic web of structure we live inside today. And the sizes of those ripples, the pattern of hot and cold across the ancient sky, encode the precise conditions of the early universe. Feed that pattern into the equations of the Standard Model, and out comes a prediction for everything that followed, including the expansion rate of the universe today. So now you have a second number, not measured locally, but predicted from the physics of the infant cosmos, projected forward across the entire age of the universe. Here is the thing that should give you chills. Those 2 numbers, the one measured by looking at nearby exploding stars, and the one predicted from the oldest light in existence, have absolutely no reason to be calculated the same way. One is direct observation in the cosmic present. The other is theoretical extrapolation from the cosmic dawn. They are separated by nearly the entire history of the universe. And for a glorious window of time, they agreed. Both of them landed in the same neighborhood. And cosmologists looked at that agreement and felt something close to triumph, because it meant the whole edifice held together. The baby photo and the grown-up universe told the same story. The model worked. That model has a name, and you should know it because it is the protagonist of this entire story and possibly its casualty. It is called lambda CDM. It's an ugly name and it stands for two ugly ideas. The CDM part means cold, dark matter. The proposal that most of the matter in the universe is not the ordinary stuff of stars and planets and people, but some invisible, unknown substance that does not glow, does not absorb light, and interacts with everything else only through gravity. We have never caught a single particle of it in a laboratory. We infer it entirely from its gravitational fingerprints. Galaxies spin too fast to hold themselves together with the visible matter alone, so something unseen must be there, holding them in. The lambda part is even stranger, and we'll come back to it because lambda is where this story detonates. For now, just hold this in your mind. Lambda CDM is the standard model of cosmology. It is to the universe what the periodic table is to chemistry. It says the cosmos is made of roughly 5% ordinary matter, everything you have ever seen or touched, about 27% invisible dark matter, and the remaining 68% something even stranger that we'll get to. With those ingredients and a handful of numbers, this model reproduces an astonishing range of observations. The pattern in the ancient light, the way galaxies cluster, the abundance of the lightest chemical elements forged in the first few minutes. For 25 years, it has been one of the most successful theories in the history of science, a 6-parameter machine that takes the baby photo of the universe and predicts the adult. People built careers on it. They built instruments to confirm it, and the more carefully they measured, the better it looked, until it didn't. The first crack was the one I mentioned at the very start. Those two numbers, the local expansion rate and the one predicted from the ancient light, stopped agreeing. Not because anyone got sloppy. The opposite. They stopped agreeing because the measurements got better. As the error bars shrank, as the uncertainty in each number tightened, the two values did not converge the way everyone assumed they eventually would. They pulled apart. The number you get from the local universe, from the exploding stars and the cosmic distance ladder, settles in at around 73. The number you get from the ancient light, run through the standard model, comes out at around 67. And the gap between them refused to close. I know that those just sound like two numbers that are kind of close. 73, 67, what's the big deal? They are in the same ballpark. But that intuition is exactly wrong, and understanding why is the key to this whole story. In science, a measurement is only as meaningful as its uncertainty. If I tell you a number is 73, but I might be off by 10 in either direction, then 67 is no problem at all. They overlap, they are consistent, move on. But these are not sloppy measurements. These are two of the most refined numbers in all of physical science, the products of decades of work by thousands of people, with their uncertainties hammered down to almost nothing. The local measurement says 73, and it is confident, to a precision that leaves almost no room. The early universe prediction says 67, and it is just as confident. And when you ask the statistics how likely it is that two measurements this precise could disagree this much by pure chance, that the gap is just bad luck, a fluke of noise, the answer that comes back is that the odds are worse than 1 in a million, possibly far worse. That is what scientists mean when they talk about the Hubble tension. It is not a vague disagreement. It is a precise, statistically violent contradiction between the universe's past and its present. Either the baby photo is lying, or the grown-up universe is lying, or, and this is the possibility that keeps people up at night, there is something happening in between, somewhere in the 13 billion years separating the two, that the standard model does not know about. Some unknown actor on the cosmic stage, changing the script without telling us. For a long time, most working astronomers assumed it would go away. It usually does. The history of cosmology is littered with anomalies that turned out to be mistakes, a miscalibrated instrument, an overlooked source of error, a subtle bias in how a sample was selected. The smart money, for years, was on a mundane explanation. Somewhere in the towering, intricate cosmic distance ladder, the argument went, there must be a flaw, some systematic error in how we measure the brightness of those pulsing stars or those exploding ones, an error that nudges the local number upward and creates a tension that isn't really there. Find the mistake, fix it, and the universe goes back to making sense. So they went looking for the mistake. They recalibrated the standard candles using a completely independent method, a different kind of star in the dying outer layers of distant galaxies, whose brightness is set by a hard physical limit and doesn't depend on the old calibration at all. The tension stayed. They used a brand new space telescope, the most powerful ever built, to re-examine the pulsing stars at the heart of the distance ladder, to check whether crowded fields or contaminating light had been throwing off the measurements for years. The tension stayed. Every time someone proposed a flaw in the local measurement and went to look for it, the flaw wasn't big enough to explain the gap. The number kept coming back around 73, and on the other side, the early universe number kept coming back around 67, confirmed and reconfirmed by multiple independent maps of the ancient light. This is the part that changed the mood in the field. It is one thing to have an anomaly. It is another thing to attack that anomaly from every angle for years with better and better tools and watch it refuse to die. Slowly, reluctantly, the conversation shifted. It stopped being a question of whose measurement was wrong and started being a question of whether the model that connects them, the model that takes the baby photo and predicts the adult, was missing something fundamental. Because if both numbers are right, then the only thing left to be wrong is the story we tell about what happened in between. And then, while everyone was still arguing about the first crack, the universe handed us two more. The second crack came from the new telescope, the one that was supposed to help. When the James Webb Space Telescope finally unfolded itself 1,000,000 miles from Earth and opened its golden eye on the cosmos, it was the most anticipated scientific instrument of a generation. It could see farther and fainter than anything before it, which meant it could see further back in time than anything before it, deep into the era of the very first galaxies, the cosmic dawn, the few 100 million years after the Big Bang, when the first structures were just beginning to ignite out of the darkness. The standard model made clear predictions about what that era should look like. Galaxies should be small, faint, few, just getting started. The cosmic web should still be assembling itself, gravity slowly gathering gas into the first modest clumps. That was the prediction, drawn straight from Lambda CDM, and everyone expected Webb to confirm it in beautiful new detail. Instead, Webb looked back into the cosmic dawn and found monsters. They were not supposed to be there. In the first few months of operation, Webb started turning up galaxies in the early universe that were far too big, far too bright, and far too mature for how little time had passed since the Big Bang. Some of them had already assembled hundreds of billions of stars worth of mass when the universe was only a few 100 million years old. An eye blink, cosmically speaking. It was as if you had taken a photograph of a city the moment after its foundations were poured, and found the skyscrapers already standing. Astronomers started calling the most extreme of them red monsters, because they glowed deep red. Their light stretched toward the infrared by the immense expansion of the universe it had crossed to reach us, and because their sheer mass was, frankly, monstrous given how early they were. To understand why this is a problem and not just a fun surprise, you have to understand how galaxies are supposed to form in the standard picture. In lambda CDM, gravity does the building and gravity is patient. First, the dark matter clumps together under its own pull, forming vast invisible halos. Gas falls into those halos, pooling at the center. And then slowly, a fraction of that gas cools and collapses and ignites into stars. But only a fraction. In the nearby universe, in galaxies we can study in detail, the process is remarkably inefficient. A typical galaxy converts only around 20% of its available gas into stars, often much less. The rest is blown away by exploding stars, heated up, scattered, lost. Star formation is a wasteful, leaky business. That inefficiency is baked into the models. It's not an assumption someone made up. It's calibrated against everything we see. Now take that inefficiency and try to build the red monsters with it. To assemble that much stellar mass that early, in the small dark matter halos that should exist at that age, the galaxies would have had to convert their gas into stars with an efficiency approaching 100%. Essentially, every atom of available gas turned into stars immediately, with almost nothing wasted. And in the most extreme cases, when astronomers ran the numbers, they found that even 100% efficiency wasn't quite enough, that to explain the most massive early galaxies, you would need more baryons, more ordinary matter, than the standard model says could possibly have been gathered into those halos in the first place. The galaxies were not just efficient. They appeared to contain more raw material than the universe was supposed to have been able to deliver to them at that point in its history. Let that sink in, because it's a genuinely strange situation. It is not merely that these galaxies formed faster than expected. It is that, taken at face value, the most extreme of them seem to require more matter, assembled more quickly than the standard model permits. And the standard model's prediction here is not a vague hand wave. It follows directly from the same physics, the same dark matter, the same initial ripples in the ancient light that made all those other successful predictions. You cannot easily pull one thread without the others unraveling. If the early universe was building structure faster than lambda CDM allows, that is not a minor footnote. That is the model failing at the one job it was supposed to be best at, telling the story of how cosmic structure grew. Now, I want to be honest with you here, because honesty is the whole point of a story like this, and because the scientists themselves are being honest about it. The red monsters are not a slam dunk. There are ways out. Maybe we are overestimating the masses of these galaxies. Measuring the mass of a smudge of light 13 billion light-years away is fiendishly hard, and it depends on assumptions about what kinds of stars are shining and how much dust is hiding among them. Maybe the early universe made stars differently than the nearby universe does. Maybe the first stars were systematically bigger and brighter, so that a galaxy could look very massive while actually containing fewer stars than it appears. Maybe there's a selection effect, where we're only seeing the rare, freakish overachievers and mistaking them for the norm, the way you'd get a distorted picture of human height if you only ever measured professional basketball players. Each of these escape routes is being actively explored, and any of them could turn out to be the answer. The red monsters alone would not bring down the standard model. But here is what makes the red monsters matter for our story. They are pushing in exactly the direction you would expect if the universe built structure faster, earlier, more vigorously than lambda CDM predicts. And remember the first crack, the Hubble tension, also has natural explanations that involve the early universe behaving differently than the model assumes, releasing or rearranging energy in ways that would change the expansion rate. Two independent anomalies, from two completely different instruments looking at completely different things, both whispering the same heresy, that the standard model gets the early universe wrong. On their own, each is just an anomaly. Together, they start to feel like a pattern, And then came the third crack, the one that, for many physicists, was the moment the whisper became a shout. To explain the third crack, I have to take you back to that letter I skipped over earlier, the lambda in lambda CDM, because the third crack is about lambda, and lambda is the strangest thing in all of physics, and possibly the strangest thing in the entire universe. In the late 1990s, two competing teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Notice the assumption built into that sentence. Everyone knew the universe was expanding, and everyone assumed it must be slowing down because the universe is full of matter, and matter has gravity, and gravity pulls things together. The expansion was like a ball thrown into the air. It would rise, but gravity would steadily decelerate it. The only real question was whether there was enough matter to eventually halt the expansion and reverse it, pulling everything back into a fiery collapse, or whether the universe would coast outward forever, slowing but never stopping. To find out, the two teams went looking at distant exploding stars, those same standard candle supernova, to measure the expansion rate far back in time and compare it to the expansion rate now. They expected to measure the deceleration. They were arguing about how much. What they found broke the universe. The distant supernova were fainter than they should have been, which meant they were farther away than they should have been, which meant that the universe, at some point in its history, had stopped slowing down and started speeding up. The expansion was not decelerating under the pull of gravity. It was accelerating. Something was pushing the universe apart, overpowering the gravity of all the matter in it. And that something was getting stronger as the universe grew. Both teams found it. They checked it against each other, terrified they had made a mistake, and they hadn't. The expansion of the universe is accelerating, and we have no idea why. We gave the mysterious push a name, and the name is a confession of ignorance. We call it dark energy. The word dark is doing a lot of work there. It does not mean black or evil or even invisible. It means we have no idea what it is. Dark energy is the placeholder we put in our equations to represent whatever it is that is causing the universe to fly apart faster and faster. And here is the truly humbling part. When you add up the cosmic budget, the 5% ordinary matter, the 27% dark matter, the remaining 68% of everything in the universe, more than 2/3 of all the energy that exists, is this: dark energy. The thing we cannot explain. We live in a universe that is overwhelmingly made of a substance we discovered by accident and do not understand. And on top of that, most of the rest is invisible dark matter we have also never directly detected. The grand total of the stuff we actually comprehend, atoms, light, you, me, every star you have ever wished on, is about 5% of reality. The other 95% is two different kinds of darkness. So what is dark energy? The simplest possible answer, the one built into lambda CDM, is that dark energy is a property of empty space itself. The idea goes all the way back to Einstein. When he wrote down his theory of gravity, the equation seemed to demand a universe that was either expanding or contracting. And Einstein, like everyone at the time, believed the universe was static and eternal. So he added a term to his equations, a fudge factor, a constant he could tune to hold the universe still against the pull of gravity. He called it the cosmological constant, and he represented it with the Greek letter lambda. When the universe turned out to be expanding after all, Einstein supposedly called the cosmological constant the biggest blunder of his life, and threw it away. And then, 70 years later, the discovery of cosmic acceleration dragged it back from the dead. Because the simplest way to explain a universe that pushes itself apart is to say that empty space has a tiny, constant energy of its own, a relentless outward pressure woven into the vacuum the same everywhere at all times, never changing. That is lambda. That is the cosmological constant. That is the most important letter in the Standard Model. And the crucial word in all of that is constant. In lambda CDM, dark energy is assumed to be exactly that, a constant. The energy of empty space does not change as the universe evolves. It was the same in the distant past as it is today, and as it will be in the unimaginable future. A galaxy's worth of vacuum has the same dark energy now as it did 10 billion years ago. This is not a small technical assumption. It is the bedrock of the whole model, the foundation everything else is built on. If dark energy is constant, then the future of the universe is sealed. The expansion will accelerate forever. Galaxies will be flung beyond each other's horizons, and the cosmos will fade into a cold, dark, lonely emptiness over timescales that make the current age of the universe look like nothing. That is the fate lambda CDM predicts. A constant dark energy means a universe that quietly, eternally dissolves. For 25 years, that assumption held. Dark energy looked exactly like a cosmological constant, exactly like the energy of empty space, exactly like Einstein's resurrected lambda. Every measurement was consistent with it being perfectly, boringly constant. And the boring answer was, in a strange way, comforting. At least we knew what kind of thing it was, even if we didn't know why it had the value it did. Then came the third crack. Then came an instrument designed to map the universe in more detail than ever before, and it looked at dark energy, and it saw it move. The instrument is called DAISY, the Dark Energy Spectroscopic Instrument, and to understand what it did you need to understand a measuring trick so elegant it feels like cheating. It is called Baryon acoustic oscillations, which is a mouthful. So let me give it to you in plain terms, because it is one of the most beautiful ideas in modern cosmology, and almost nobody outside the field has heard of it. Go back to the early universe, the hot, dense plasma fog before the cosmic microwave background was released. In that fog, the slightly denser regions, the seeds of future galaxies, were being squeezed by gravity pulling inward and pushed back by the pressure of the hot radiation trying to escape. This tension set off sound waves, real, physical pressure waves, rippling outward through the plasma of the infant universe at a significant fraction of the speed of light, like the ringing of a struck bell, except the bell was the entire cosmos. These waves expanded outward in spheres from every dense seed for hundreds of thousands of years. And then, abruptly, the universe cooled, the fog cleared, the pressure that drove the waves vanished, and the waves froze in place. Each one left behind a shell, a ring of slightly enhanced density at a very specific radius, the exact distance the sound wave had traveled before it stopped. That radius is a fixed, known length. It is set by simple physics in the early universe, and it is the same everywhere. Cosmologists call it a standard ruler, and here is the magic. Galaxies preferentially form in those slightly denser shells. So if you map the positions of millions and millions of galaxies across the sky and across cosmic time, you will find that they are very slightly more likely to be separated by that one specific distance, the frozen radius of those ancient sound waves. It's a faint statistical preference, invisible to the eye, buried in the noise of 100 million galaxies, but it is there, and it is rock solid. You have a ruler of known length, printed across the entire universe at every era of cosmic history. Measure how big that ruler appears at different distances, at different times in the past, and you can trace the entire expansion history of the universe with extraordinary precision. You can ask, era by era, exactly how fast space was stretching. And because dark energy is what drives that stretching, the expansion history is a direct readout of how dark energy has behaved over billions of years. That is what Daisy was built to do. It sits atop a telescope in Arizona, and it is a marvel of engineering. 5,000 tiny robotic positioners, each one swinging an optical fiber into place to catch the light of a single galaxy or quasar, retargeting the entire array every 20 minutes, night after night, harvesting the spectra of millions upon millions of objects spread across billions of light years and billions of years of cosmic time. No survey in history has mapped the three-dimensional structure of the universe on this scale. It was designed to measure that standard ruler at many different distances, and from those measurements to pin down the behavior of dark energy more tightly than ever before. Everyone expected it would do what every previous experiment had done: confirm with greater precision that dark energy is a constant, that it is Einstein's lambda, that the standard model holds. In its first major release of results, and then again, more dramatically, with its second release built on the first 3 years of data, the largest map of the universe's structure ever assembled, Daisy did not confirm that dark energy is constant. It found hints, and then stronger hints, that dark energy is changing over time. That in the distant past, dark energy may have been stronger than it is now, and that it has been weakening as the universe ages. That the relentless, unchanging vacuum energy of the standard model is not unchanging at all. That lambda, the constant, the bedrock, the most important letter in cosmology, might not be a constant. I need to be careful and precise here, because this is the crux of the entire story, and it is easy to overstate. Daisy did not announce that they had proven dark energy is evolving. What they found is that, when you combine their map of the cosmic ruler with the ancient light of the cosmic microwave background, and with those standard candle supernova, the combination prefers a universe where dark energy changes over time, over a universe where dark energy is constant. The preference is statistically significant. Depending on exactly which set of supernova data you fold in, it ranges from a modest signal to one strong enough that, if it holds up, it would be a genuine discovery. It is not yet at the gold standard level of certainty that physicists demand before they will say something is real. But it is well past the level where you can comfortably ignore it, and it has been replicated and strengthened, not weakened, as more data has come in. The signal did not fade with scrutiny. It grew. And now hold all 3 cracks in your mind at once, because this is the moment the story turns from a collection of curiosities into something that genuinely rattled the field. Crack 1. The expansion rate of the universe measured locally and predicted from the early universe refused to agree, and the disagreement has survived every attempt to make it go away. Crack 2. The very first galaxies are too big, too bright, too mature, built too fast, as if structure assembled more vigorously in the early universe than the model allows. Crack 3. Dark energy, the dominant component of the entire cosmos, the thing the standard model treats as an eternal constant, shows signs of changing over time. 3 independent instruments, 3 independent phenomena: the cosmic distance ladder, the deep field galaxy surveys, the largest 3-dimensional map of cosmic structure ever made. They were not designed to talk to each other. They have no shared source of error that could fake all 3 at once, and every one of them is pointing, in its own language, toward the same unsettling conclusion: that lambda CDM, the most successful theory in the history of cosmology, is incomplete. That there is something in the universe, in its beginning, in its expansion, in the dark energy that fills it, that we have fundamentally failed to account for. That convergence is why people who spent their careers defending the standard model are now standing up at conferences and saying carefully, with their reputations on the line, that we may be living through the early days of a scientific revolution. Not a tweak, a revolution. The kind that happens maybe once a century, where a picture of reality that seemed complete cracks open and reveals that it was only ever an approximation of something deeper that we are only now glimpsing. So let me do the thing that honest science demands, the thing the loud voices online almost never do. Let me try as hard as I possibly can to make all of this go away. Let me give you the case for boredom, because the most likely outcome, historically, is still that some or all of these anomalies dissolve under scrutiny, and you deserve to understand why a careful person would bet that way. Start with dark energy, the third crack, the biggest one. The evidence that dark energy is evolving is not a single clean measurement. It is the product of stitching together three very different kinds of data: the cosmic ruler from Daisy, the ancient light from the microwave background, and the standard candle supernova. And the strength of the signal depends heavily on which set of supernova you use. There are several rival supernova catalogs, compiled by different teams using different telescopes and different methods of accounting for the subtle ways these explosions vary. Plug in one catalog, and the evidence for evolving dark energy is strong. Plug in another, and it weakens dramatically, to the point where the data is once again perfectly consistent with a boring, constant lambda. That is a red flag. When a profound conclusion about the nature of reality flips depending on which of several imperfect datasets you trust, the responsible reaction is not excitement. It is suspicion. It suggests the signal might not be coming from the universe at all, but from some subtle, unaccounted-for systematic error in how we calibrate exploding stars. Some of the most respected statisticians in cosmology have argued exactly this: that the evolving dark energy signal is most likely an artifact of supernova systematics, not a property of the cosmos. There is an even deeper subtlety, and it's worth understanding because it shows you how careful you have to be. The way Daisy tests whether dark energy is constant involves fitting the data to a specific, simple mathematical form, a particular equation with two knobs that describe how dark energy might change over time. That form is a convenient choice, not a law of nature. It was picked because it's simple and flexible, not because anyone believes dark energy must obey it. And when you let those two knobs vary and ask the data which settings it prefers, it leans away from the constant. But that doesn't necessarily mean dark energy is evolving in any real, physical sense. It might mean that this particular two-knob equation is just slightly the wrong shape, and the data is compensating in a way that mimics evolution. Fitting flexible curves to noisy data and finding a preference for the flexible curve is exactly the kind of result that has fooled scientists before. The history of physics is full of 3 sigma signals, results that looked just significant enough to be exciting, that evaporated when more data arrived. Most 3 sigma anomalies are flukes. That is not cynicism. It is the measured base rate, learned the hard way over a century of particle physics and cosmology. Now do the same demolition job on the red monsters. As I said before, measuring the mass of a galaxy 13 billion light-years away is brutally hard. You are looking at a faint red smudge, and to turn that smudge into a number for stellar mass, you have to assume things. What mix of stars is producing the light? How much dust is reddening it? How the light has been stretched by cosmic expansion. Change those assumptions, and the mass can swing by large factors. Several of the most alarming early mass estimates have already come down as astronomers gathered better data. Some of the apparent monsters turned out to be smaller galaxies whose light was contaminated by an actively feeding black hole at their core, which made them look far brighter and more massive than they really are. And there's the deeper possibility I mentioned, that the first generation of stars was genuinely different, heavier, hotter, brighter per unit mass. so that early galaxies could blaze with the apparent brightness of giants while actually weighing far less. None of these explanations require touching the foundations of cosmology. They only require admitting that we don't yet fully understand how the first stars and galaxies formed, which is hardly a radical confession. The red monsters might be telling us something new about astrophysics, the messy, complicated business of how gas turns into stars, without saying anything at all about the deep structure of the universe. And the Hubble tension, the oldest and most stubborn crack. Even here, the boring explanation isn't dead. The local measurement rests on that towering distance ladder, rung after rung, each one calibrated against the one below it, and an error anywhere in that chain propagates all the way to the top. People have hunted for that error for years and not found one big enough, but absence of a found error is not proof there isn't one. The early universe measurement, meanwhile, depends entirely on the standard model being correct, which is precisely the thing in question. If the model is even slightly off in the early universe, the predicted expansion rate shifts. It remains possible that the tension is the sum of several small, mundane errors on both sides that happen to push in the same direction. Unlikely, but not impossible. Extraordinary claims require extraordinary evidence, and overturning the standard model of cosmology is about as extraordinary a claim as exists. So that is the case for boredom, and I want you to take it seriously, because the scientists take it seriously. Any one of these anomalies on its own would most likely be filed under interesting puzzle, probably a systematic error, check back in 5 years. That has been the fate of most cosmic anomalies. The graveyard of cosmology is full of revolutions that never happened. But, and it's a big but, the reason this moment feels different to the people inside the field is not any single one of these anomalies. It's that they are showing up together, and they are showing up in a particular pattern, and they are not going away. For most of the last century, when cosmology had a problem, it had one problem at a time in isolation, and the problem usually had the courtesy to either resolve itself or stand alone. What's happening now is different in character. You have multiple independent probes measuring different things, with different instruments, run by different teams who would love nothing more than to be the one to debunk the others. And they are not contradicting each other. They are reinforcing each other. They are all gently insisting that the early universe behaved a little differently than the standard model says, and that the dark energy filling the cosmos is not quite the eternal constant we assumed. When errors are random, they point in random directions. When independent measurements start pointing the same way, you have to start taking seriously the possibility that they are pointing at something real. And there's a subtler reason this moment carries weight, which is that the anomalies aren't just coexisting. In some cases, they might be connected. This is the part that genuinely excites theorists. Suppose, for the sake of argument, that dark energy is not constant. Suppose that in the very early universe, before the cosmic microwave background was released, there was an extra dose of some dark energy-like substance, a brief, early burst of repulsive energy that then faded away. Theorists have a name for this idea, early dark energy. And here is the remarkable thing. If you add a pinch of early dark energy to the standard model, it changes the physics of that ancient plasma in exactly the right way to shift the predicted expansion rate, to nudge the early universe number up from 67 towards 73. In other words, a single new ingredient, an evolving dark energy that was once stronger and then weakened, could potentially explain the Hubble tension and the Daisy results at the same time. And a universe that expanded slightly differently in its first moments might also have built its structure on a slightly different schedule, which could bear on the red monsters. One new idea, threading through all three cracks. That is the kind of thing that makes a physicist's pulse quicken, because that is what real new physics looks like when it first appears. Not as a single clean signal, but as a constellation of stubborn anomalies that suddenly, eerily, line up. I don't want to oversell this. Early dark energy is one candidate among many. It has its own problems, and the various anomalies don't yet snap together into a single tidy picture. The honest state of the field is messier than that, but the possibility, the mere live possibility that these separate mysteries are facets of one deeper truth, is why the mood has shifted from annoying systematic error to we might be standing at the edge of something. So let's step over that edge for a while. Let's take the data at face value, suspend the skepticism, and ask the question that should be making the hair on your arms stand up. What if it's real? What if dark energy really is changing? What would that actually mean, not in the abstract, but for the universe, for its history, for its future, for the ultimate fate of everything that exists? Start with what it does to our picture of the present. If dark energy is evolving specifically, if it was stronger in the past and is weakening now, which is roughly what the data hints at, then we are living through a special and fleeting era of cosmic history. The acceleration that those two supernova teams discovered, the speeding up that overturned everything in the 1990s, might be a temporary phase. It might be slowing down. We could be sitting at a turning point, a hinge in the life of the cosmos, where the great outward push that has dominated recent cosmic history is beginning to lose its grip. To have arrived, as a species, at the exact moment when we develop the instruments to measure dark energy, and to find that dark energy is changing right now, in our cosmic era, would be a coincidence so striking that it borders on the uncomfortable. It would mean we are not looking at an eternal, fixed background. We are watching the universe in the middle of an act, now extended to the future, because this is where it gets genuinely vertiginous. The entire fate of the universe, how it ends, billions and trillions of years from now, depends almost entirely on what dark energy does. And if dark energy is not constant, then every prediction about the end of everything is back on the table. In the standard picture, with constant dark energy, the future is settled and it is bleak. The expansion accelerates forever. Galaxies beyond our local group recede faster and faster until they cross a horizon and vanish from view, their light stretched into nothing, gone forever. The stars burn out. New stars stop forming. The galaxies fade. Black holes slowly evaporate over timescales with more zeros than you can comfortably contemplate, and the universe drifts into a state called heat death. Cold, dark, empty, maximally disordered. Every usable scrap of energy spent, nothing left that can ever happen again. A universe that doesn't end with a bang or even a whimper, but with an endless, featureless, frozen silence. That is the future that constant dark energy writes for us. It is the future in most textbooks. But change dark energy and you change the ending. Suppose dark energy keeps getting stronger over time instead of weakening, a possibility some versions of the data don't fully rule out. Then you get a far more violent end, with a name that sounds like science fiction but is taken entirely seriously: the Big Rip. In this scenario, the repulsive force of dark energy grows without limit. First, it tears apart the clusters of galaxies. Then individual galaxies are pulled to shreds, their stars flung into the void. Then solar systems are dismantled, planets ripped from their stars. Then the planets themselves are torn apart, then atoms, then the nuclei of atoms, then the very fabric of space stretched to infinity in a finite time. Everything that has ever been bound together by any force is, in the final instant, unbound. The universe doesn't fade away. It is shredded. And the truly disturbing part is that, if this is the future, it has a date, a specific, calculable number of years from now, When the rip arrives, far away, almost incomprehensibly far, but finite, or go the other way. Suppose the Daisy hint is right and dark energy is weakening, and suppose it keeps weakening and eventually does more than weaken. Suppose it flips sign and turns from a repulsive push into an attractive pull. Then the acceleration doesn't just stop, it reverses. The expansion of the universe grinds to a halt and begins to run backwards. Galaxies that have been fleeing each other for billions of years begin to fall back together. The universe contracts, slowly at first, then faster, the sky growing brighter and hotter as everything rushes inward, until all of creation collapses back into the single fiery point it began as. We call this the Big Crunch. And some theorists go further still and imagine that the crunch could rebound into a new Big Bang, that the universe could be cyclic, expanding and contracting and expanding again, an eternal cosmic heartbeat with no true beginning and no true end. Constant dark energy forbids this. Evolving dark energy might allow it. Do you see what's at stake now? This is not an argument about a decimal place. The question of whether dark energy is constant or evolving is the question of how the universe ends. It is the difference between a slow, cold fade, a violent shredding, and a fiery collapse that might be followed by rebirth. For 25 years, we thought we knew which ending we were headed for. We had picked the cold fade, the heat death, with reasonable confidence. And now 3 independent instruments are quietly suggesting that we may have been reading the wrong ending all along, that the book of the universe has a different final chapter than the one we'd written in, and we are only now, in the last few years, getting our first real glimpse of what it might actually say. And it goes deeper than the fate of the cosmos, because if dark energy evolves, then we don't just need a new ending. We need new physics. Einstein's cosmological constant, the energy of empty space, the same everywhere and always, is mathematically the simplest possibility, and it requires no new ideas, just a number. But a dark energy that changes over time cannot be the energy of empty space, because the energy of empty space, by definition, doesn't change. So it would have to be something else. And the leading candidate for that something else is an idea borrowed from particle physics, that the universe is filled with a new kind of field, a sort of invisible energy field permeating all of space, whose strength can evolve as the universe expands. Theorists call it quintessence, after the ancient idea of a 5th element beyond earth, water, air, and fire, a 5th essence filling the heavens. If quintessence is real, it would be a new fundamental component of nature, as basic as the electromagnetic field, completely unknown until now, and we would have detected its existence not in a particle collider, but by watching the expansion of the entire universe over billions of years. And quintessence is only one of the doors that opens if these anomalies hold. There is a more radical possibility, one that some physicists find even more tantalizing, and others find frankly heretical. What if the problem isn't dark energy at all? What if dark energy doesn't exist, and dark matter doesn't exist, and the reason we keep inventing invisible substances to fill 95% of the universe is that we've been using the wrong theory of gravity all along? This is worth pausing on because it cuts to the heart of how science can go astray. Remember how we discovered dark matter and dark energy in the first place? We didn't see them. We inferred them. We took our theory of gravity, Einstein's general relativity, the most beautifully tested theory in the history of physics, and we applied it to galaxies and to the expansion of the universe, and the equations didn't balance. Galaxies rotated too fast for the visible matter to hold them together, so we added invisible dark matter to make the equation work. The universe accelerated when it should have decelerated, so we added invisible dark energy to make that equation work too. In both cases, We kept the theory of gravity sacred and invented new, undetectable stuff to save it. But there has always been a minority of physicists who point out that there is another way to balance an equation. Instead of adding mystery substances to the left side, you could modify the law on the right side. Maybe gravity itself behaves differently on the vast scales of galaxies and the cosmos than it does in the solar system where we tested it. Maybe Einstein's theory, magnificent as it is itself only an approximation, perfect on human and planetary scales, but subtly wrong across billions of light years. If that's true, then dark matter and dark energy are not substances at all. They are illusions, artifacts of forcing the universe to obey a law it doesn't quite obey. They are the ghosts that appear when you use the wrong map. Modifying gravity is a heavy thing to attempt because general relativity is so spectacularly well tested, and most attempts to change it break something that works. But the cracks we've been talking about are exactly the kind of evidence that breathes life back into these ideas. If the expansion history of the universe doesn't quite match what dark energy predicts, and if structure formed differently than the standard model says, then maybe, the issue is not the contents of the universe, but the rules it runs on. Various modified gravity theories make their own predictions for how dark energy should appear to evolve and how galaxies should assemble, and some of them can mimic exactly the signals DAISY and JWST are seeing. We don't know if any of them are right. Most of them probably aren't. But the point is that the anomalies have pried open a question we thought was closed. Whether the foundation of all our cosmology, the theory of gravity itself, is the final word, or just our current best approximation of something deeper. This is the part of the story I find genuinely thrilling, and I want to share why, because it connects to something true about how science actually advances, as opposed to the tidy myth of steady progress we're often told. Science does not move forward by confirming what we already believe. It moves forward at the anomalies, at the places where the data refuses to fit. The great revolutions in physics did not begin with someone discovering something entirely new out of the blue. They began with a stubborn little discrepancy that everyone else was trying to explain away. Consider the planet Mercury. For most of the 19th century, astronomers had a problem with Mercury's orbit. It didn't quite trace the path that Newton's law of gravity predicted. The orbit slowly rotated, precessed, by a tiny amount more than the calculations allowed, a discrepancy so small it sounds absurd to care about, a few arcseconds per century, a whisper of a wobble. And for decades, everyone assumed it was a mundane problem. Maybe there was an undiscovered planet closer to the sun, tugging on Mercury. They even named it in advance Vulcan and went looking for it. They never found it. The tiny discrepancy sat there, unexplained, an irritation in the corner of an otherwise triumphant theory of gravity that had successfully predicted the existence of Neptune and described the heavens with breathtaking precision. Most astronomers shrugged and assumed it would be cleared up eventually. And then a patent clerk in Switzerland rewrote our understanding of space and time. And when Einstein applied his new theory of gravity to Mercury, the tiny extra wobble fell out of the equations exactly. The anomaly that everyone had been trying to sweep under the rug was, in fact, the first fingerprint of a completely new conception of reality. The discrepancy wasn't noise. It was a doorway. The same thing happened at the dawn of quantum mechanics. Physicists in the late 19th century were trying to calculate the light emitted by a hot object, a piece of glowing metal, say. Their theories, the proud classical physics of the era, predicted that such an object should emit an infinite amount of energy at short wavelengths. Obviously absurd. Furnaces do not vaporize you with infinite ultraviolet light. They called this failure the ultraviolet catastrophe, And it was a small, embarrassing crack in the otherwise gleaming structure of classical physics. To fix it, a reluctant physicist named Planck proposed a desperate mathematical trick. That energy comes not in a smooth flow but in discrete, indivisible packets. He thought it was just a calculational fudge. It turned out to be the foundation of quantum mechanics, the theory that would utterly transform our understanding of matter, energy, and reality itself. And that underpins essentially every piece of technology you are using to watch this. Again, the revolution didn't come from a grand new vista. It came from a small, stubborn place where the numbers refused to behave. That is the pattern, over and over, throughout the history of physics. The future doesn't announce itself with trumpets. It hides in the discrepancies, in the anomalies, in the boring little places where the data is just slightly, persistently, infuriatingly wrong. And the scientists who change the world are usually not the ones who make some spectacular new observation. They are the ones who refuse to look away from a small disagreement that everyone else has decided to ignore. So when I tell you that the Hubble constant is off by a few units, or that some galaxies are a bit too massive, or that dark energy might be drifting by a small amount, I am describing exactly the kind of thing that, historically, precedes an earthquake. Not always. Usually these things really do turn out to be systematic errors. But sometimes, just sometimes, the small crack is the edge of a continent we didn't know was there. I want to tell you what this actually feels like for the people living through it, because the human side of this story rarely gets told, and it's more interesting than the equations. Imagine you have spent 30 years of your life building, defending, and refining a theory. You wrote your dissertation on it. You taught it to a generation of students. You designed instruments to confirm it, won grants on the promise of confirming it, staked your professional reputation on its correctness. And now, in the twilight of your career, the data you fought to collect is whispering that the theory you devoted your life to is incomplete. That is not an abstract intellectual event. It is a deeply human one. It involves pride and fear, and the particular vertigo of watching the ground you stood on for decades begin to soften. And the remarkable thing, the thing that should restore some of your faith in the enterprise of science, in an age when faith in institutions is hard to come by, is that these scientists are reporting the anomalies anyway. They are not hiding them. They are not burying the inconvenient results. They are standing up at the largest physics conferences in the world and presenting evidence that threatens their own life's work, and then inviting their colleagues to try to tear it apart. The DAISY collaboration did not announce that they had overturned lambda CDM. They announced, carefully and with all the appropriate caveats, that their data prefers an evolving dark energy, and then they released the data so that anyone on Earth could check it. That is the system working exactly as it is supposed to. The skeptics who argue it's all supernova systematics are not enemies of the discovery. They are part of the discovery, doing the essential, unglamorous work of trying to kill the result so that, if it survives, we can trust that it's real. Science is not a collection of facts. It is an adversarial process, a structured argument that grinds on across years and continents. And the beautiful, almost miraculous thing about it is that it is designed so that even the people with the most to lose are incentivized to tell the truth. But here is the honest, slightly maddening reality of where we are right now. We do not know. We are in the uncomfortable middle of the story, the part that no documentary can resolve for you, because the universe has not finished answering. The evidence is suggestive, in some cases strong, but not yet decisive. The anomalies are real in the sense that they are really in the data, but whether they reflect a flaw in our instruments, a gap in our understanding of stars and galaxies, or a genuine crack in the foundations of physics, is a question that has not yet been settled. Anyone who tells you they know for certain that the standard model is dead is getting ahead of the evidence. And anyone who tells you for certain that it's all just systematic errors and there's nothing to see here is also getting ahead of the evidence. The truth is that we are watching, in real time, one of those rare moments when a field holds its breath. So how do we find out? How does a story like this actually end? Not with an argument, but with more data. And the data is coming. This is the part that should excite you the most, because we are not going to be left wondering forever. Right now, a new space telescope is mapping billions of galaxies across a third of the entire sky, specifically to measure the expansion history of the universe and the behavior of dark energy with unprecedented precision. Another space observatory is being prepared to do complementary work, measuring vast numbers of supernova and the cosmic ruler with exquisite accuracy. A giant new telescope on a mountaintop is beginning a decade-long survey that will image the entire visible sky every few nights, catching millions of exploding stars and watching the structure of the cosmos evolve. DAISY itself is still running, still mapping, its dataset growing larger and its measurements sharper every year. And the James Webb Space Telescope continues to stare into the cosmic dawn, gathering better spectra of those early galaxies, pinning down their true masses, resolving whether the red monsters are really as impossible as they first appeared. Within a few years, not decades, years, these instruments are going to deliver verdicts. If dark energy is truly evolving, the signal will sharpen, climb past the threshold of certainty, and become undeniable, and we will know, with the full weight of scientific confidence, that the standard model is incomplete and that we live in a universe whose deepest component changes over time. And if it's a systematic error, that too will become clear. The signal will fade as the data improves, the anomaly will dissolve, and Einstein's cosmological constant will be vindicated once again, as it has been so many times before. Either way, we are going to find out. The question is going to be answered in our lifetime, probably within this decade. We are not the generation that gets to wonder forever. We might be the generation that gets to know. Think about what a strange privilege that is. For nearly all of human history, the questions we are discussing were not even askable. How old is the universe? What is it made of? How will it end? Is it eternal, or does it have a final chapter? Every culture that has ever existed told stories to fill that void, because the void was unfillable. And now, in this narrow sliver of time, we have built machines that can actually measure the answers, that can read the baby photo of the cosmos, weigh the first galaxies, and clock the expansion of space itself across billions of years. We are the first humans with the tools to catch the universe in the act of doing something we didn't expect, to be alive at the exact moment when 3 independent instruments start hinting that the textbook is wrong, and to have the means to test it. That is not a small thing. That is one of the most extraordinary positions any generation of our species has ever been in. And I haven't even told you about the other cracks, because the 3 I've focused on, the Hubble tension, the early galaxies, and evolving dark energy, are the headliners, but they are not alone. Once you start looking, the standard model has a number of smaller bruises, and a few of them are worth knowing about because they thicken the plot. There's a tension hiding in how clumpy the universe is. The standard model, fed the pattern from the ancient light, makes a precise prediction for how lumpy the universe should be today, how strongly matter should have clustered into galaxies and clusters, and the great cosmic web over billions of years. We can measure that clumpiness directly by mapping how the light from distant galaxies is subtly bent and distorted by the gravity of all the matter it passes on its way to us, a technique called weak gravitational lensing, which lets us weigh the invisible dark matter by the way it warps space. And when we do, several of those surveys find that the universe is just slightly less clumpy than the standard model predicts. Not dramatically, but persistently. The early universe, as seen in the ancient light, seems to predict a little more structure than the late universe actually shows. It's a smaller signal than the Hubble tension, and it has wobbled as data has improved. Some recent measurements have eased it. But it's another place where the bridge between the early universe and the late universe groans under the load, where the baby photo and the adult don't quite line up. Then there are the neutrinos, and this one is genuinely bizarre. Neutrinos are ghostly particles, almost massless, that stream through the universe in unimaginable numbers. Trillions are passing through your body every second, harmless, barely interacting with anything. We know from laboratory experiments that they have a tiny but non-zero mass. That much is settled physics. Cosmology can also weigh them in a sense, because the total mass of all the neutrinos in the universe affects how structure forms. Heavier neutrinos smooth out the cosmic web slightly, so you can use the universe itself as a scale. And when Daisy collaborators put the universe on the scale, they got a strange answer. Assuming the standard model, the cosmic measurement of the neutrino mass came out implausibly low. So low that, with some methods, it pushed toward a physically impossible negative value, as if the universe contained less structure smoothing than even zero-mass neutrinos would produce. That's a contradiction, a sign that something in the assumptions is off. And here's the kicker. If you allow dark energy to evolve, if you drop the assumption that lambda is constant, the neutrino weirdness eases. The impossible negative mass relaxes back toward a sensible value. So even this obscure corner of the data, the cosmic weight of the lightest particles in existence, is quietly pointing in the same direction as everything else, toward a dark energy that isn't constant. The anomalies keep rhyming. I bring these up not to overwhelm you, but to make a point about the texture of the situation. This is not one anomaly that a single clever explanation might dissolve. It is a constellation of tensions, some large, some small, some that have grown and some that have faded, clustered around the seams of the standard model, around the places where the early universe is stitched to the late universe, and where the assumption of a constant dark energy is load-bearing. A theory in perfect health doesn't have a constellation of tensions. It has the occasional fluke that comes and goes. What we have now looks less like flukes, and more like a pattern of stress fractures around a foundation that may have been carrying more than it can bear. Now let me take you down into the deepest and most uncomfortable part of all of this. The part that I think most people never fully confront even when they hear about dark matter and dark energy. We have been talking about these as if they are details to be refined. They are not details. They are an admission, written into the foundations of our best theory, that we do not understand what the universe is made of. Step back and look at the whole picture. The standard model of cosmology, the triumphant, successful, precise theory we've been defending this whole time, says that everything we have ever observed, every star, every galaxy, every atom, all the ordinary matter in existence, adds up to about 5% of the universe. 5%. The other 95% is divided between dark matter, which we have never detected in any laboratory despite decades of increasingly sensitive experiments built specifically to catch it, and dark energy, which we cannot explain at all and which, if these new results hold, doesn't even behave the way we assumed. Sit with the strangeness of that. We have built a model that works, that predicts the ancient light and the clustering of galaxies and the cosmic abundance of elements with stunning accuracy. And the price of that working model is that 95% of its content is stuff we have given names to precisely because we cannot describe it. Dark matter and dark energy are not explanations. They are labels for our ignorance, dressed up in the language of physics. We are like someone who has worked out the exact rules of a card game by watching thousands of hands, who can predict the outcomes with perfect reliability, but who has never been allowed to look at the faces of the cards. We know how the universe behaves. We have almost no idea what it is. For decades, we tolerated that ignorance because the model worked so well. As long as the label stayed put, as long as dark matter behaved like simple invisible matter and dark energy behaved like a simple constant, we could hold our noses and use them, confident that the explanations would come eventually. The new anomalies threaten that comfortable arrangement. If dark energy is evolving, then even our placeholder for the largest component of the universe is wrong. We don't just not know what it is. We had the wrong idea about how it acts. And that should make you wonder, with a kind of cold humility, how much else of our confident picture is built on labels we've mistaken for understanding. There's a famous worry in cosmology that physicists sometimes whisper to each other, only half joking. What if we are like the ancient astronomers who built ever more elaborate systems of circles within circles to describe the motions of the planets, the epicycles, and made them fit the observations beautifully, with great precision, for over 1,000 years, all while being fundamentally, completely wrong about the basic structure of the solar system? Their model worked. It made accurate predictions, and it was built on a false picture of reality, a picture so deeply assumed that questioning it seemed absurd, until someone finally did. Dark matter and dark energy might be our epicycles, clever fixes that make the equations balance while concealing a deeper truth we haven't yet been willing to see. Or they might be perfectly real, and we might catch the dark matter particle next year and explain dark energy the year after, and the standard model might sail on, vindicated into the future. We genuinely do not know which of those worlds we live in, and the anomalies we've been discussing are the first hard evidence that might finally tell us. Let me slow the whole thing down for a moment and take you to the place where one of these cracks actually lies, because I think the numbers can numb you, and it helps to remember that behind every data point is a real and almost unbearable physical reality. When the James Webb Space Telescope captures the light of one of those red monsters, think about what is actually happening. That light left the galaxy more than 13 billion years ago, when the universe was an infant, a few 100 million years old. At that moment, there was no sun, there was no earth, there was no carbon, no oxygen, none of the heavier elements that would one day make up your body, because those elements had not yet been forged in the hearts of stars and scattered by their deaths. The atoms that are reading these words right now did not exist in any recognizable form. And from that galaxy, in that ancient era, a packet of light set out across the void. For 13 billion years it traveled, while the universe expanded around it, stretching its wavelength longer and longer, shifting it from visible light down through the spectrum into the deep infrared. While that light was in transit, our entire solar system formed from a collapsing cloud of gas. While that light was in transit, the first life appeared on Earth, and the dinosaurs rose and fell, and the continents drifted, and our ancestors climbed down from the trees and learned to make fire and build cities, and finally, in the last cosmic instant, to launch a golden telescope into the cold, 1,000,000 miles above the planet. And that telescope opened its eye at exactly the right moment to catch that one ancient photon at the end of its 13 billion year journey. The light we are studying is older than the Earth, older than the sun, older than the elements we are made of. To look at the cosmic dawn is quite literally to look at the past, not a representation of the past, but the actual, original light of it, arriving now. And what that light is telling us is that the early universe was already busy, already building, already lighting up with galaxies that have no right to be so grown. The era we're peering into is the time when the first stars in the universe were igniting, ending the long darkness that followed the Big Bang. What astronomers poetically call the cosmic dark ages, the hundreds of millions of years when the universe had cooled below the glow of its birth, but the first stars had not yet switched on. The cosmic dawn is the moment that darkness ended, when the first light since the Big Bang began to shine, and the radiation from those first stars and galaxies began to tear apart the neutral gas filling the universe, reionizing it, making it transparent, lifting the final veil. We are watching the universe turn on its first lights, and the standard model said those lights should be coming on slowly, hesitantly, a few faint sparks at first. What Webb is showing us is closer to a sky already filling with fire. The dawn was brighter and earlier and more vigorous than the model predicted. Maybe that's because we misjudged the brightness of the first stars. Or maybe it's because the universe in its first moments was running on physics we haven't yet written down. I want you to also appreciate something about the precision involved here, because it's the precision that turns these anomalies from curiosities into crises. We tend to think of cosmology as a soft science, full of hand-waving about billions and billions. It is the opposite. Modern cosmology is one of the most precise sciences that has ever existed. When cosmologists measure the pattern of ripples in the ancient light, they are measuring temperature differences across the sky of a few millionths of a degree, and they map them across the entire celestial sphere. From that map, they extract the fundamental parameters of the universe: its age, its composition, its geometry, its expansion rate, to a precision of better than 1%. The age of the universe is known to be about 13.8 billion years, and the uncertainty on that number is only a few tens of millions of years. We know the age of all of creation to better than 1%. That is not vague. That is a level of precision that would have seemed like sorcery to astronomers a century ago, who couldn't agree on the age of the universe within a factor of 2. It is precisely because the measurements are this good that the disagreements matter. If our tools were crude, a gap between 67 and 73 would mean nothing. They'd both be lost in the fog of uncertainty. But our tools are not crude. They are razors. And when two razor-sharp measurements of the same quantity disagree, you cannot wave it away. You are forced to confront it. The Hubble tension is not a sign that cosmology is sloppy. It is a sign that cosmology has become so precise that it can now detect cracks that were invisible before. We have entered the era of precision cosmology, and the strange, almost ironic consequence of all that precision is that it has revealed problems that lower precision would have hidden. We built instruments good enough to confirm our theory beyond any doubt, and in doing so, we built instruments good enough to break it. There's a thought here that I find genuinely dizzying, and it has to do with our place in time. If dark energy really is evolving, if it was stronger in the past and is weakening now, then we are living at a peculiar moment. The acceleration of the universe, the dominance of dark energy over matter, only began relatively recently in cosmic history. For most of the universe's life, matter was in charge, and the expansion was decelerating. It's only in the last several billion years that dark energy took over and the expansion began to accelerate. And we, the only known observers in the universe, the only minds capable of measuring any of this, happen to have arisen and built our telescopes during this brief window when dark energy is in transition, when its effects are detectable, when the balance between matter and dark energy is roughly even. A little earlier in cosmic history, and dark energy would have been too feeble to notice. A little later, and the accelerating expansion will have swept all the other galaxies beyond our horizon, leaving future astronomers in our galaxy with an empty sky. No evidence of expansion at all. No cosmic microwave background within reach. No way to ever discover the Big Bang. They would look out and see only our own island of stars in an apparently static, eternal void. And the entire history we've reconstructed would be permanently lost to them. We are, in a real sense, living in the golden age of cosmology, not just because of our technology, but because of when we exist. The universe has left the evidence lying around for us, for now in this window, and it will not always be so. That coincidence that we are here, with these tools, at exactly the cosmic moment when the deepest secrets are still legible, is either a profound stroke of luck or a clue to something we don't yet understand about our relationship to the cosmos that made us. At this point, a fair question is gnawing at you, and I'd be doing you a disservice if I didn't address it head-on. What does any of this actually change for you? You are going to close this video and go back to your life. The bills will still be due. The world will look exactly the same tomorrow whether dark energy is constant or not. The expansion of the universe operates on scales so vast and timescales so long that no discovery about it will ever alter a single thing about your day. So why should you care? Why should anyone pour billions of dollars and thousands of careers into measuring a number that will never change the price of bread? I think the honest answer is also the most important one, and it's not the answer that tries to justify the science by pointing to spin-off technologies, though those are real. The honest answer is that this is one of the few human endeavors that is purely, defiantly about wanting to know. Not wanting to profit, not wanting to win, wanting to know. We are a species that woke up on a small wet rock circling an ordinary star in the suburbs of an unremarkable galaxy, among hundreds of billions of galaxies. And instead of accepting our smallness, we asked how old it all is. We asked what it's made of. We asked how it began and how it ends. And astonishingly, impossibly, we have started to get real answers, not myths, not guesses, but measured, tested, precise answers, wrung out of the faint light of dying stars and the cold afterglow of creation. The question of whether dark energy is constant is the question of what kind of universe we live in and how our story ultimately ends. It is the question of whether everything fades to cold silence, or is torn apart, or collapses, and perhaps begins again. To not care about that is to not care about the largest context of your own existence. It is the frame around every other picture. And the fact that we, briefly conscious arrangements of stardust, can not only ask the question but build machines to answer it, that is, to me, one of the most dignified things our species does. There's something else too, something about how to hold a question like this, that I think matters more than ever in the world we live in now. We are surrounded constantly by people who are absolutely certain that everything is a conspiracy, certain that the experts are lying, certain that they alone have seen through the illusion. And the seductive thing about that certainty is that it feels powerful. It feels like knowledge, but it is the opposite of knowledge. Real knowledge, the kind these scientists are pursuing, is built on the willingness to say the three hardest words in any language. I don't know. The cosmologists at the center of this story are not claiming to have overturned reality. They are doing something far braver and far harder. They are sitting in the uncomfortable middle, holding a genuine uncertainty, refusing to collapse it prematurely into either triumphant revolution or dismissive denial. They have evidence that something might be wrong with their deepest theory, and instead of either ignoring it or overhyping it, they are patiently, rigorously, collectively working to find out which it is. That is the discipline of not knowing. It is the engine of every real discovery our species has ever made. And it is the exact opposite of the cheap, loud certainty that fills so much of our world. So if you take one thing from all of this, let it be that. Not the specific numbers, those will be refined, and some of what I've told you will be revised as the data improves, because that's how it's supposed to work. Take the posture, the willingness to look directly at a crack in everything you believe, to neither flinch away from it nor leap to conclusions about it, but to ask, carefully and honestly, what is really going on here? The scientists in this story did not find the answer. They found a better question, and they are pursuing it with everything they have. That is what discovery actually looks like from the inside, before the textbooks tidy it up into a clean tale of triumph. It looks like confusion held with discipline. It looks like a handful of people staring at numbers that don't add up and refusing to look away. Let me bring it all back together now, because we've traveled a long way, and I want you to leave holding the whole shape of it in your mind at once. For 25 years, we had a model of the universe that worked. It told us the cosmos is 13.8 billion years old, made of 5% ordinary matter, 27% invisible dark matter, and 68% a mysterious dark energy that we assumed was a perfectly constant property of empty space, the resurrected ghost of Einstein's greatest blunder. That model predicted the ancient light, the clustering of galaxies, the abundance of the elements, with breathtaking precision. It was one of the towering achievements of the human mind. And then the cracks appeared. The expansion rate of the universe, measured by looking at nearby exploding stars, refused to agree with the rate predicted from the oldest light in existence. A contradiction so sharp and so stubborn that, after years of hunting for a mistake, the mistake could not be found. The first galaxies, glimpsed by the most powerful telescope ever built, turned out to be too big, too bright, too mature, built too fast, as if the early universe had assembled its structures more vigorously than the model could allow. And the largest map of the cosmos ever made looked directly at dark energy, the dominant component of all reality, the thing assumed to be eternal and unchanging, and found that it might be evolving, weakening over time, behaving like nothing in the standard model permits. 3 instruments, 3 phenomena, no shared source of error, all of them in their separate languages, pointing at the same heresy, that the model is incomplete, that something fundamental is missing, that the universe is not quite what we thought it was. There's a longer arc to this story that I think gives it its real weight, and it's worth pulling back to see it. Every few centuries, humanity discovers that it is smaller and stranger than it thought, and each time the discovery feels like the floor giving way. We once believed the Earth sat motionless at the center of all things, with the sun and stars wheeling around us. Then Copernicus moved us off the center, made us one planet among several, circling the sun. That was a demotion, and people resisted it fiercely because it cost us our specialness. Then we learned that the sun itself is just one star among hundreds of billions in our galaxy, not central, not special, an ordinary star in the galactic suburbs. Then, less than 100 years ago, astronomers were still arguing whether our galaxy was the entire universe, until it was shown that those faint smudges in the sky were not clouds within our galaxy but other galaxies, island universes of their own, and suddenly our galaxy became one among hundreds of billions. Each step, we got smaller. Each step, the universe got vaster and less concerned with us. And each step, after the initial vertigo, we found that the larger, stranger universe was more magnificent than the cozy one we'd lost. The standard model of cosmology might be setting us up for the next step in that long demotion. Because here's the thing about the version of the story we've believed for the last quarter century. It still let us feel like we understood. Yes, 95% of the universe was dark and mysterious, but at least the rules were simple: a constant dark energy, a simple dark matter, a clean and final model into which the last details would eventually be slotted. The new evidence threatens even that consolation. It raises the possibility that the universe is not running on the simple rules we wrote down, that its largest component changes over time, that our theory of gravity itself might be an approximation, that we have been looking at epicycles and calling them understanding. If that's true, it would be another demotion, not of our place in space this time, but of our confidence in how much we know. We would have to admit that even our best, most precise, most triumphant theory was only ever a way station, and that the real universe is deeper and stranger than the clean picture we'd grown comfortable with. And if history is any guide, that would not be a tragedy. It would be a beginning. Every time the floor has given way, what we found beneath it was a richer reality than the one we'd lost. A universe with evolving dark energy, or a new fundamental field of quintessence, or a modified law of gravity operating across cosmic scales, would not be a poorer universe than the one in our textbooks. It would be a vastly more interesting one. It would mean there is new physics waiting to be discovered, a new force or field or principle as fundamental as electromagnetism, hidden in plain sight in the expansion of space itself. It would mean the story isn't over. It would mean that the generation alive right now, possibly some young person watching this who hasn't yet chosen what to do with their life, will be the one to write the next chapter, to find the theory that explains why dark energy changes, to catch the dark matter particle at last, to draw the new map that replaces the one we've been using. The cracks are not the end of cosmology. They are an invitation. Imagine, for a moment, the physics textbook of 100 years from now. There's a real chance it contains a chapter that doesn't exist yet, a chapter about the early 21st century, about the years when a telescope at 1,000,000 miles found galaxies that were too old, when a map of millions of galaxies caught dark energy changing, when two stubborn numbers refused to agree, and when all of it together finally forced humanity to abandon the standard model and reach for something deeper. That chapter would describe our moment the way our textbooks now describe the discovery of Mercury's wandering orbit, or the ultraviolet catastrophe, as the small, stubborn anomalies that everyone tried to explain away, until someone realized they were the first signs of a new universe. The students reading that chapter will know how the story ends. They'll know which theory won, which anomalies were real and which dissolved, what dark energy turned out to be. To them, it will be settled history, a clean tale with a tidy conclusion. They will not be able to feel what it was like to live inside the question, before the answer existed, when nobody knew. But we can. We are living inside it right now. We are the people in the chapter before the chapter has been written, and we get to watch it happen. Of course, and I keep coming back to this because intellectual honesty demands it, that imagined textbook chapter might say something completely different. It might say that in the early 21st century, there was a flurry of excitement over some apparent anomalies in cosmology, that the evolving dark energy signal turned out to be an artifact of supernova calibration, that the early galaxies turned out to be ordinary once their masses were measured correctly, that the Hubble tension yielded to a subtle systematic error finally found in the distance ladder, and that the standard model, lambda CDM, emerged from the whole episode stronger and more vindicated than ever. Einstein's cosmological constant confirmed yet again. That chapter is equally possible, maybe more possible. The smart historical bet is still on the anomalies dissolving, because that's what most anomalies do. And there would be something almost as profound in that outcome, a testament to how astonishingly robust our understanding has become, that even our most precise instruments, pushed to their absolute limits, find nothing that breaks it. To survive this level of scrutiny would itself be a kind of triumph for the standard model. The point is that we don't know which textbook we're writing, and that not knowing is not a failure of the story. It is the story. We are standing at a genuine fork, with real evidence pointing down a path that might lead somewhere extraordinary, and we have not yet walked far enough to see where it goes. Before we close, I want to take you all the way to the end, to each of the endings. Actually, because this is where the abstract question of whether a number is constant becomes something you can almost feel. And because the whole reason any of this grips us is that it is, ultimately, about how the story finishes. 3 possible endings hang on the behavior of dark energy. Let me show you each one. The first ending is the quiet one, the one the standard model predicts if dark energy is truly constant. The far future in this scenario is a story of slow, irreversible loss. Right now, when you look up, you can see thousands of stars, and on a dark night, the faint smudge of the Andromeda galaxy, the nearest large galaxy to our own. But the accelerating expansion is carrying the distant galaxies away from us faster and faster. And there will come a time, tens of billions of years from now, when they have receded beyond the cosmic horizon, so far that the space between us and them is expanding faster than light can cross it, and their light can never reach us again. One by one, the galaxies will wink out of view, not by dying but by vanishing over the edge of the observable universe, until the sky outside our own local group of galaxies is utterly empty and black. Then, over far longer timescales, the stars themselves will exhaust their fuel. Star formation will sputter and stop as the gas runs out. The last stars will be small, cool, red dwarfs, burning slowly for trillions of years, and then they too will fade to embers. The galaxies will go dark. What remains, dead stars, black holes, cold, wandering planets, will drift in an expanding blackness, and over timescales so vast that the numbers lose all meaning. Even the black holes will evaporate, leaking away their mass as faint radiation, until nothing is left but a thin, cold, ever-thinning gas of particles in an endlessly growing void. This is the heat death, a universe that doesn't die in fire but in cold and dark and silence and distance. Every fire gone out, every distance grown infinite, nothing left that can ever change again. It is, if dark energy is constant, the most likely fate of everything. The second ending is the violent one, and it happens if dark energy is not constant but growing stronger over time without limit. This is the big rip, and it is genuinely the most disturbing future in all of physics because it has a deadline. As dark energy intensifies, its repulsive force begins to overpower the forces that hold things together, starting with the weakest bonds and working its way down. First, in the final billions of years, the great clusters of galaxies are pried apart. Then, as the rip accelerates, individual galaxies begin to dissolve, their stars scattered into the widening dark. In the last months before the end, our own galaxy would come apart, the stars flung away from one another. In the final hours, the solar system would be dismantled, the planets torn from their orbits around the sun. In the last minutes, planets themselves, worlds, would be ripped apart, their matter exploded outward. And in the final fraction of a second, the rip would reach down to the smallest scales, tearing apart molecules, then atoms, then the nuclei within atoms, then the very fabric of space and time, stretched to infinity in a finite instant. Everything that has ever been joined to anything would be, in that last moment, utterly and finally unjoined. This is what some of the data leaves on the table if dark energy is evolving in the wrong direction. Not silence, but annihilation. Not a fade, but a scream. The third ending is the one that turns the whole story around, and it becomes possible if dark energy is weakening, which is roughly the direction the new data hints at. If dark energy continues to weaken, and eventually does more than weaken. If it dwindles to nothing and then reverses, turning from a push into a pull, then the expansion of the universe will slow, stop, and begin to run backwards. After billions of years of everything flying apart, everything would begin to fall back together. The distant galaxies, instead of receding, would start to approach. The cosmic web would contract. The sky would slowly brighten and warm as the universe compressed, as the ancient light that has been cooling for billions of years began to blue shift and heat up again, until the whole sky blazed, and all of creation rushed back toward a single point, hotter and denser and brighter, until the universe ended as it began, in a fireball, the Big Crunch, the Big Bang in reverse. And some theorists dare to imagine that this is not truly an ending at all, that the crunch could rebound into a new expansion, a new bang, a new universe rising from the ashes of the old, in an eternal cycle of birth and death and rebirth that has been going on forever and will go on forever, with our entire universe just one breath in an infinite cosmic respiration. We don't know if that's possible. The physics of a bounce is uncertain and contested, but evolving dark energy is what cracks the door open to it, and a constant dark energy slams it shut. 3 endings: cold silence, violent annihilation, or fiery collapse and possible rebirth. And which one is real, which future is actually written for the universe you live in and everything it contains, comes down to the behavior of that one component, dark energy, and specifically to whether it holds constant or changes over time. That is the stakes of the question Daisy is asking. That is why a hint that dark energy might be evolving is not a footnote in a journal. It is a possible revision of the final chapter of reality. For 25 years we thought we knew the ending. We had settled on the cold silence, with reasonable confidence. And now the universe is whispering that we may have read the wrong page. I keep using the word whispering, and I want to be precise about why, because it captures something true about the strange emotional register of this whole moment. This is not a story with a triumphant announcement at the center. There was no single morning when someone walked into a room and said the standard model is dead. Here is the proof. That is not how it happened, and that is not how real science usually happens, despite what the movies suggest. What happened instead was quieter and in a way more profound. A signal appeared in one dataset, faint, intriguing, easy to dismiss. Then it appeared in another, slightly stronger. Then a different team, using a different method, found attention pointing the same way. Then the new telescope found the impossible galaxies. Then the big map firmed up the dark energy hint. No single thunderclap, just a slow accumulation of unease, building across years and across the whole community, until one day people looked up and realized that the mood had changed, that the questions being asked at conferences were no longer how do we confirm the model, but what if the model is wrong? And that these questions were being asked not by outsiders or cranks, but by the very architects of the theory. If you went to one of the big cosmology meetings right now, you would feel it. You'd see the field split, good-naturedly but genuinely, into camps. There are the ones who think we are on the verge of something historic, who look at the convergence of anomalies and feel the electricity of a paradigm about to shift, who are already racing to build the theories that might replace or extend the standard model. And there are the careful skeptics, often the most senior and battle-scarred people in the room, who have watched anomalies come and go for decades, and who are quietly confident that this too will resolve into systematic errors, who keep reminding everyone that 3 sigma signals are a dime a dozen, and that the graveyard is full of revolutions that were announced too soon. And then there's everyone in between, holding both possibilities at once, genuinely unsure, waiting for the data. What you would not find, and this is the thing I want you to appreciate, is consensus that the standard model has fallen. That consensus does not exist because the evidence does not yet support it. The field is doing the honest, difficult thing, holding the tension, refusing to resolve it before the data resolves it, letting the argument play out the way it's supposed to. And the argument is not bitter mostly, which is its own quiet miracle. The skeptics and the revolutionaries need each other. The revolutionaries push the field to take the anomalies seriously, to build the new theories, to imagine the universe might be stranger than we thought. The skeptics push the field to scrutinize every measurement, to hunt down every possible systematic error, to make sure that if a revolution is declared, it's a real one. Both are doing science. Both are necessary. The whole machine only works because they are pointed at each other. And the friction between them is exactly what grinds the truth into focus. When you read a headline that screams scientists baffled or theory in crisis, what's actually happening underneath is this: a vast, distributed, self-correcting argument carried out by thousands of people across the planet, designed from the ground up to be hard to fool, slowly, methodically converging on whatever the real answer turns out to be. It is not chaos. It is the most reliable truth-finding process our species has ever built, and you are watching it work on one of the biggest questions it has ever faced. So where does that leave you, having come all this way with me? Not with an answer. I'm not going to insult you by pretending the question is settled, because it isn't, and anyone who tells you otherwise in either direction is selling certainty they don't have. What I can give you instead is something better than a false answer. I can give you the question in its full and genuine form, the way the scientists themselves are holding it right now. Is the universe the way we thought it was, or is it not? Is dark energy the eternal, unchanging energy of empty space, or is it something alive and evolving that we've barely begun to understand? Did the standard model just get its first real wound, the kind that precedes a revolution, or is it about to survive its hardest test and emerge stronger than ever? We do not know, but we are going to find out. With these instruments in these years, almost certainly within your lifetime. The data is being collected right now, tonight, while you sleep. The robotic positioners are swinging into place atop that mountain in Arizona. The new telescopes are scanning the sky. The answer is, quite literally, on its way to us across the dark, in the light of distant galaxies that left them billions of years ago and is only now arriving. There's one more thing I have to tell you, because without it you can't fully understand why some physicists are quietly relieved by the idea that dark energy might be evolving. Why? For a certain kind of theorist, an evolving dark energy isn't a disaster at all, but a possible escape from an embarrassment that has haunted physics for decades. To get there, I have to show you what is probably the single worst prediction in the entire history of science. And I mean that literally, not a figure of speech. The worst prediction ever made. It concerns that constant dark energy, the cosmological constant, the energy of empty space. Here's the problem. According to our best theory of the very small quantum mechanics, quantum field theory, the framework that describes particles and forces with extraordinary precision, empty space is not truly empty. The vacuum is a seething, restless thing. At the smallest scales, particles are constantly flickering in and out of existence, borrowing energy from the void and paying it back in fleeting instants, a perpetual quantum foam of activity that never stops. And all that activity should have energy. The vacuum, according to quantum theory, should have an energy of its own. Exactly the kind of energy that could act as a cosmological constant. Exactly the kind of thing that could drive the acceleration of the universe. So physicists did the natural thing. They calculated how much energy the quantum vacuum should contain, and then they compared it to the amount of dark energy we actually observe pushing the universe apart. The two numbers did not agree. They disagreed by a factor of 10, followed by about 120 zeros. The theoretical prediction for the energy of empty space is larger than the observed value of dark energy by something like 10 to the power of 120. That is not a number you can even meaningfully picture. It is so vastly, catastrophically larger than the observed value that if the vacuum energy were really that big, the universe would have torn itself apart in the first instant after the Big Bang, before a single atom could form. There would be no galaxies, no stars, no chemistry, no us. The fact that we exist at all means the real value is almost unimaginably smaller than the theory predicts. This staggering mismatch is known as the cosmological constant problem, and it is widely regarded as the deepest, most humiliating unsolved problem in all of theoretical physics. Our two greatest theories, quantum mechanics for the very small, general relativity for the very large, when forced to talk to each other about the energy of empty space, produce an answer that is wrong by 120 orders of magnitude. We have simply learned to live with this, the way you learn to live with a crack in your ceiling you can't afford to fix. We use the observed value, we ignore the catastrophic prediction, and we try not to think too hard about the abyss it reveals in our understanding. Now you can see why some theorists look at evolving dark energy with something like hope. Because if dark energy is a constant, if it really is the energy of empty space, then we are stuck with that monstrous mismatch. And we have to explain not only why the vacuum energy is so much smaller than predicted, but why it happens to have the one precise tiny value that allows galaxies and life to exist. That's two miracles to explain. But if dark energy is not the energy of empty space, if it's instead something dynamic, like quintessence, a field that evolves over time, then the whole problem might be reframed. Perhaps the true energy of the bare vacuum is zero, canceled out by some symmetry or mechanism we haven't discovered, and the thing we call dark energy is something else entirely, a separate field with its own modest energy that has nothing to do with the catastrophic vacuum calculation. In that case, an evolving dark energy wouldn't just be a new discovery. It might be a clue to solving the worst problem in physics. The anomaly that looks like it's breaking the standard model might actually be pointing toward a deeper theory that finally makes sense of the vacuum. That is why, for all the caution and skepticism, there is an undercurrent of genuine excitement. The cracks might not just be damage, they might be the first light coming through from a better theory on the other side. And that reframes the whole stakes one final time. We have been treating the constant dark energy of the standard model as the safe, comfortable, well-understood option, and the evolving dark energy as the dangerous, revolutionary one. But in truth, the constant was never comfortable. It was always sitting on top of that 120 orders of magnitude abyss, a number we could measure but never explain, the single most precisely fine-tuned and least understood quantity in physics. Maybe the universe has been trying to tell us all along that our picture of empty space is wrong, and the DAISY results are simply the first time we've built an instrument sensitive enough to hear it. Or maybe not. Maybe the constant holds, the abyss remains, and we go on living with the crack in the ceiling. We don't know, but the possibility, the live, testable, imminent possibility that the answer to the worst problem in physics is hiding in the expansion of the universe, waiting for the next few years of data to reveal it, is the kind of thing that makes a person want to stay up all night reading papers or watching the sky. Think back to where we started. That single number, the one almost no one had ever thought about, holding up the entire story of where we came from and how it ends. The expansion rate of the universe. For a quarter of a century, two ways of measuring it agreed, And in that agreement, we read a kind of permission to believe we understood our cosmos. And then the agreement broke, and it didn't break because anyone got sloppy. It broke because we got too good. We sharpened our instruments past the point where the universe could keep its secret. And the secret it gave up was that something doesn't fit. One number became two numbers that won't reconcile. And around that first crack, others appeared, galaxies too old for their age, a dark energy that won't hold still, a constellation of smaller tensions all leaning the same way, until the cumulative weight of it became impossible for the field to ignore. What you have to understand, the thing I most want you to carry away from all of this, is that none of this is decay. This is not science failing. This is science working exactly as it is meant to, at the highest level it has ever operated. A theory that could not be questioned would not be science. It would be dogma. The standard model of cosmology earned its place by making predictions so precise that they could, in principle, be proven wrong. And now, for the first time, the universe is testing whether they are. That is not a crisis in the sense of a collapse. It is a crisis in the older, truer sense of the word. A turning point, a moment of decision, the point in a story where everything that comes after depends on what happens next. We are at the crisis. And the beautiful, almost unbearable thing about being alive right now is that we get to watch it resolve in real time with our own eyes, instead of reading about it in a book where the ending is already known. There is a particular kind of person, and maybe you are one of them, who hears a story like this and feels not anxiety but exhilaration. Because what it really says is that the universe is not finished surprising us. We thought we had it mostly figured out: 5% matter, 27% dark matter, 68% a tidy constant, and a clean march toward cold silence. And the universe looked at our confident little model, and in the faint light of dying stars and the patient mapping of millions of galaxies said, "Not so fast. There is more here than you know. There is something in the dark you have not yet understood. Come and find it." That is not a threat. That is the single most thrilling sentence the cosmos can speak to a curious species, and we are hearing it right now, more clearly than any generation before us. We are made of the stuff that came out of the Big Bang, processed through generations of stars. The atoms in your body were forged in stellar furnaces and scattered by stellar deaths long before the Earth existed. We are, in the most literal sense, the universe that has organized itself into something that can look back at itself and ask questions. And the questions we are asking now: what is dark energy? How does the universe end? Is our deepest theory of reality complete, or only an approximation of something stranger? Are the universe, through us, trying to understand itself? When Daisy measures the expansion of space, when Webb stares into the cosmic dawn, when a cosmologist stands at a podium and admits that the numbers no longer agree, that is the cosmos becoming aware of its own nature, one careful measurement at a time. We are not separate from this story. We are how the story knows it's being told. So no, I cannot tell you tonight whether the standard model will fall. I cannot tell you whether dark energy is constant or evolving, whether the universe ends in silence or fire or rebirth, whether the textbook of the future will record our moment as the dawn of a revolution, or as the episode when the old theory proved its strength one more time. Nobody can tell you that yet. The honest answer, the only answer that respects both you and the truth, is that we are in the middle of finding out, and the finding out is happening now. And it is one of the great adventures of our time, unfolding quietly in observatories and on mountaintops and in the cold, a million miles above your head while the world goes about its business below. But here is what I can tell you, and I'll leave you with it. For the first time in the history of our species, the questions that every human being who ever lived has gazed up at the night sky and wondered about: how big, How old, how it began, how it ends are no longer the territory of myth and guesswork. They are measurable. They are being measured, and the measurements are coming back strange. The universe has handed us a set of clues that don't quite fit the story we told ourselves, and instead of looking away, we are leaning in. Somewhere out there, in data already collected and data still arriving on beams of ancient light, the answer is waiting. We are closer to it than anyone has ever been. And whether it confirms everything we believed or overturns it completely, one thing is already certain. We are living through one of those rare moments when the universe is about to teach us something genuinely new about what it is. The evidence is in. The verdict is coming. And nothing, not the model, not the textbooks, not our picture of how it all ends, is guaranteed to look the same on the other side. Keep watching the sky. The most interesting chapter hasn't been written yet, and we are the ones holding the pen.